Hello, my name is Christiane Schmidt. I'm from Linköping University, and I'll be talking about guarding polyominoes under K-hop visibility or minimum K-dominating sets in grid graphs. And that research is funded by Sweden's innovation agency, Vinnova, within the project Network Optimization for Car Sharing Integration into a Multimodal Transportation System. So what's the agenda for today? First, I'll motivate and formally define the problem. Then I'll present NP completeness results. Then I'll move over to app gallery theorem type results, and I'll finish with open problems. So what's the motivation of our problem? So let's assume we want to serve a city with car sharing stations. And the demand is given in the granularity of square cells. So we'll overlay our map with square cells. And we assume that customers are willing to walk a certain distance, and we assume that this distance is the same over the complete city. So no matter if we're in the city center or on the outskirts of the city, we're always willing to walk the same distance to reach a car sharing station. And of course, that's a very simplified version of assuming demand. And what we will do in the project is we'll use a multi-agent simulator, MATSIM, to actually obtain a more detailed representation of the demand and how that reacts to car sharing stations. But with that, will work for today. So what does that mean for us? We can represent the city as a polyomino, and walking is only possible within the boundary of the polyomino. Why? Well, if you look in particular at Stockholm, then any holes represent water bodies, and we can simply not walk through them. And then our goal is to place as few car sharing stations as possible to serve the complete city. So what can a station serve then? Well, we know that we have this walking range, so a unit square can serve all the unit squares that are reachable within this walking range. Let's say our walking range K equals 5, then we have this green unit square there, and it can reach all, or it can serve, in this case, as a car sharing station, all the light green unit squares. And if we consider that as a visibility, then actually for K larger or equal to 2, this means that we can look around corners. So this green unit square there, if you go across that bridge, then it can look around the corner onto the land there. How do we formally define that? Well, first we need to formally define a polyomino. So a polyomino is a connected polygon in the plane that is formed by joining unit squares, and in our case, m unit squares on the square lattice. And we can build the dual graph, and the dual graph of a polyomino is a grid graph. And then a unit square is K-hop visible to another unit square if the shortest path between these two in the dual grid graph has length at most K. So in this example, U and V can see each other if K equals 3 or if it's larger than 3. And so here we have an example of a visibility region of a unit square. The green one is the one where we place a guard, and then the light green is the visibility region of that unit square. And then we can formulate our problem, which is the minimum K-hop guarding problem, or the MKGP. We're given a polyomino, we're given a range K, and we want to find the minimum cardinality unit square guard cover in P under K-hop visibility. And if you remember the title of my talk, then there's actually an alternative formulation of this problem, and that's in terms of minimum K-dominating sets. So for the minimum K-dominating set problem, we're given a graph, and we want to find a minimum cardinality set dk, which is a subset of the vertices, so that each vertex in the graph is connected to a vertex in the subset dk with a path of length at most k. And the minimum K-dominating set problem is NP complete in general graphs. And here we're interested in the problem in grid graphs, because as you remember, that's a dual of a polyomino. So the first result that I like to present is on NP completeness. And we'll start with K equals 2. So the MKGP is NP complete for K equals 2 in polyominoes with holes. The reduction is from planus reset. And just to check that the problem is actually in P, if we are given a set of guards, then we can easily verify if every unit square is indeed covered by those guards. So the problem isn't in P, we only have to show NP hardness now. So for our reduction from planar 3 set, we build gadgets. We build variable gadgets. We build corridor gadgets to propagate our truth assignments of the variables, and we build class gadgets. We have a variable gadget, and we can connect different corridors to that depending on if the variable is set to true or false. And here we have the blue one in case the variable appears in the clause, and the red one in case the negated variable appears in the clause. And for this variable gadget, which we can, of course, elongate if we want to connect more corridors, there are two true settings, two assignments of guard positions, which use the smallest number, the minimum number of guards possible, which is in this case are 6 guards. And this one we consider equivalent to setting the variable to true, and this one we consider equivalent setting the variable to true. And as you can see, we always have either setting to true, we have 2 unit squares covered in the left corridor, and if we set it to false, we have 2 unit squares covered in the right corridor and none in the other. We can easily bend corridors just at any position, independent of how we come in there. We can always just connect. And then, of course, we still need the class gadget. So we have the corridors that propagate the truth assignment to the variables. And then we have a class gadget where we have those corridors coming in from the top, from the right, and to the from the bottom. So let's look at the different cases here. We consider first the variant where all variables have a truth assignment that does not fulfill the clause, and the light red part still is part of the visibility region of these guards. What we can do then is we can place 3 witnesses colored in yellow, pink, and turquoise that have pairwise disjoint visibility regions. So we definitely need at least 3 guards to cover the remainder of that class gadget. And in fact, we can do with those 3 guards. So 3 guards are necessary and sufficient in case we have 3 variables that are not fulfilling the clause. If we have at least one set to a truth assignment that is fulfilling the clause, so it's always the blue one, where in blue you have the guard position, and light blue is its visibility region. Then again, we have 3 cases depending on in which corridor we have the one fulfilling the clause. And what we can say is that 2 guards in this case are both necessary and sufficient, so we can't do better, but we also need that many. And then we have the case where we have 2 variables set to a truth assignment that is fulfilling the clause. And again, we can do with 2 guards, and we do need 2 guards. Then the final case is when we have all our variables having a truth assignment that fulfills the clause. So again, the blue ones are the guards, and we have in light blue the visibility regions. We again can place 3 witnesses. They now they are not really witnesses. They don't have pairwise disjoint visibility regions, but what we know is that there's no guard that can see all 3 squares. So we need at least 2 guards to cover the remainder of the class gadget. And in fact, we can do with 2 with these 2. So we have again that 2 guards are necessary and sufficient. And what we have with that is that in all the cases where we have at least 1 variable having a truth assignment fulfilling the clause, we need 2 guards. And if we have none that fulfills this, we need 3 guards. And with that, our reduction is complete. And just to give you an idea how that would look like, here we have an example of 3 variables and the clause V1 or V2 or not V3. And in green, we have the 2 guards in the clause. Again, we have an equivalent formulation. So the equivalent formulation of the theorem is that the minimum 2 dominating set problem is NP complete in grid graphs. And in fact, we can also show that our guarding problem under K of visibility is NP complete for K equals 1 in polyominoes with holes. Again, the reduction is by from planar 3 set. If we're given a set of guards, we can easily verify if it's in fact a guard set. So this remains the same. Again, we will construct variable gadget connected to corridors, and the corridors will propagate our truth assignment and will have class gadgets. So the variable gadget here is a very simple one. It's just a 2 by n box. Again, we have those different corridors, which we can connect several of. And we have 2 placement of unit square guards that use the smallest possible number of unit square guards in this gadget. Again, we say that this one is equivalent to setting the variable to true, and this one is equivalent to setting the variable to false. And now we have that 1 unit square in the corridor is covered or not. The corridor bending works as before. That doesn't really matter how wide our visibility regions reach. And then we have, again, a class gadget. This one, now we have the corridors, the variable corridors connecting to the left, the top, and the right. And the idea is exactly the same. So if we have no variable having a truth assignment fulfilling the class, so here it's always, again, the light red that indicates the visibility region, and the red that you still see, at least there on the left-hand side, that's the actual location of the unit square guards. Then here we have 3 witnesses that have pairwise disjoint visibility regions, and we can cover them with 3 guards, the remaining parts. So 3 guards are necessary and sufficient for this case. And for the other cases, again, we can show that 2 guards are necessary and sufficient. This is for having 1 variable in blue, having a truth assignment fulfilling the class. This is for having 2 of them. And then again, if we have all of them having a truth assignment fulfilling the class, then here the blue ones are the positions of the unit square guards. The light blue is the visibility region. We can now place 2 witnesses, and here it's really witnesses. So they have pairwise disjoint visibility regions. We know that we need at least 2 guards to cover the remainder of the class gadget, and in fact we can do with 2 guards. So again, we have that if we have at least 1 variable having a truth assignment that fulfills the clause, we need 2 guards to cover the clause. If we have none, we need 3 guards. And again, that finishes our proof or our reduction. And just again, to have an overview, so this is an example of the same class, V1 or V2 or not V3, and we have 2 guards in the class gadget in green. And again, we can use the equivalent formulation. So we can say that the minimum 1 dominating set problem is NP complete in grid graphs with holes. With that, let's move over to art gallery theorems. So we want to give bounds on the number of guards that are always sufficient and sometimes necessary to cover polyominoes of a specific class. And we'll look at generally polyominoes here. The first one says that there exist simple polyominoes with m unit squares that require m over k plus 1 rounded down many unit square guards to cover their interior under k-hop visibility. So m over k plus 1 rounded down many are sometimes necessary. And the proof is quite easy. We build a comb-like structure where we have our row of unit squares and we attach spikes to the top and to the bottom alternatingly, always of length k. And the pink unit squares here are witnesses. They have pairwise disjoint visibility regions. So we know that we need to place at least 1 in each of these visibility regions. And in fact, we can cover everything by placing just unit square guards along the center row. And this is of course for the case that m is divisible by k plus 1. So if it's not, then we just add the remaining unit squares to the right of our shaft of our row of unit squares. And if we place the rightmost unit square guard at that in our shaft, then it can also see this row. So we have the sometimes necessary bound. And now we'll formulate an actually Articular theorem. So we have a tight bound of m over k plus 1 guards being always sufficient and sometimes necessary to cover polyominoes with m unit squares under k-hop visibility for k equals 1 or k equals 2. And we give constructive proofs, but we only need the always sufficient part because the sometimes necessary part we just covered. So for k equals 1, what we do is we use a dual grid graph and we build a matching, a maximum matching in here. That's the black one here. We know that every vertex in our dual grid graph that's not matched is adjacent to matched vertices only. Otherwise, we can extend our matching. In fact, in this example, we have exactly one unmatched vertex. And if we have a matching edge, then all unmatched vertices are adjacent, all of them either to B or all of them to W, so not to both of them. So what will we do for each matching edge? We place a guard at the unit square that is adjacent to unmatched vertices, if it exists, and otherwise just on one of the two. And with that, we get our m/2 bound. So how do we go for k equals 2? We kind of use the same idea. We just build one layer on top. So we compute a maximum matching in our dual grid graph, and then we build a graph, the pink one on top of it, where we have a vertex for every matching edge and for every unmatched vertex. And two vertices are connected by an edge. If both of our vertices represent an edge in the original dual grid graph, then if any of the vertices are connected by an edge in our original graph, and if one of them represents an edge and the other a single vertex, well, then if the single vertex has an edge to one of the two edges that are represented by the edge. And then what we do is we again compute a maximum matching now in this graph GM. And then what we do is we argue how we can place our guards by a case distinction. So, and I'm not going to go through all of them, just to some of the example cases. So let's say both vertices in our matching edge represent an edge each in the original grid graph, and they are not adjacent to any other unmatched vertices. Then we can just place a single guard at one of the vertices that now represents or that yield the edge in our new graph, and that single guard covers 4 unit squares. Now let's say we still have both of them representing an edge, but they are adjacent to unmatched vertices, but all these unmatched vertices represent a single vertex from the dual grid graph. And let's assume that without loss of generality, all these unmatched vertices are adjacent to V U prime. So the vertex that represents the vertices U and U prime in the original grid graph. And then, so the first case here is that the edge UW or the edge UW prime are in the original, the edges of the original grid graph, but U prime W and U prime W prime are not. And then we might have some additional unmatched vertices, but we know that we at least have one that is adjacent to U prime. And again, this light gray ones might be present or not, but however it is, if we place single guard on U, it will cover U, U prime, W, W prime, and at least one such unmatched vertex. So we have a single guard covering at least 5 unit squares. And if the case is that our edges are parallel, then we place a single guard on either U or U prime, and it will again cover at least 5 unit squares. And then we have several other cases where 2 guards cover at least 6 unit squares, a single guard covers 3, covers at least 4, covers at least 5, covers at least 5, covers at least 2 guards cover at least 6, and a single guard covers at least 5 unit squares. And if we consider all of these cases, what we have is that each guard covers at least 3 unit squares. So m/3 rounded down, which is m/k+1 rounded down, many guards are always sufficient. And with that, let me come to the open problems. So of course, open is a computational complexity in simple polyominoes, or equivalently in grid graphs without holes, and upper bounds on the number of guards for k larger or equal to 3. So this always sufficient type of statement. And completely open approximation algorithm. So of course, for k equals 1, we get a very trivial 4/2 approximation by the matching construction, but that is kind of not really interesting. And with that, I would like to say thank you for your attention, and I'm happy to answer your questions.